Yeah, so it's not difficult to start with this morning, I don't think. Why the heck are those in there? Doesn't seem right. Oh well. Okay, density. I'll write that down. Got that? Yeah. We know this word already, don't we? We've seen it before. But we're just going to look at it in a little bit more detail. So we've seen the formula already. What's the formula? Do we remember? That's the unit, yeah. What's the formula?
Mass times volume.
Say that again? You sure?
Mass over volume.
Mass over volume. We remember that's mass over volume. No, you don't need to write that down again if you have it already. You think you all have this, don't you?
Is it lead?
Length.
Oh, length.
Oh, it's all falling out of your brain. Long break, huh? And the unit is kilograms per meter cubed. Cubed, yes. Yes. Oh, it's been a long week. A long, long week. So, what exactly does this tell us? Like, what exactly is density? Mm-hmm. No, I just mean, like, what does it tell us about the material? Like, what are you saying when you're saying the density?
How much mass in a certain volume?
Yeah, so like, what is that? Yeah, well, just simply, like, it's how compact, yeah. How close together it is, how compact it is. You know, like how, well, compact is really the best word, isn't it? How squished together it is, yeah? So, some materials have a high density, obviously, and, well, maybe you can tell me, what materials do you think might have a high density? Yeah, like, what examples?
Metals.
Yeah, give me examples.
Lead.
Lead, yep. Iron, yeah. What else?
Heavier metals.
Yeah. What about valuable metals? Gold and silver and things like that. So gold, for example, has a density of, does anybody know actually? So it's 19,320 kilograms per meter cubed. This means that per unit meter cubed, there's a lot of gold, you have 19,320 kilograms, in case you forgot what gold was. As a little warm-up question, what I want you to do for me, here I have the density as 19,320 kilograms per meter cubed. I would like you to convert that to, what do you think I'm going to ask?
Centimeters.
Yeah, and not only that, but grams per centimeter cubed. Do that for me. See if you remember how on earth to do that.
Grams is...
Oh, I got a new phone.
Hey.
It's called a smartphone.
Wow,
You
welcome
see?
to the...
This is my first smartphone. It's my first smartphone.
Has it changed your life?
I don't know if it's changed my life. It's made some things different.
It's very useful, you'll find.
Moto G, only 5 years old.
What age?
You have an answer, but you don't look happy with it.
Kilo is 10 to the minus 3.
What did you get?
3.
10 to the power what? Oh, that's way off. Anyone else? This makes teacher worried and sad.
19.32.
Correct. 19.32. Do we forget How to do this?
No.
No.
You multiply by the fraction of kilograms divided meters, or well, grams divided centimeters.
Yeah. Multiply by kilo, divide by centi cubed. So it's multiply 1,000 and divide by
100.
0, or I'll have to write it down. What's wrong? You look unhappy with this.
That's
Do you want me to do it quickly?
1 million. 1 million.
Am I doing it or not doing it?
Please do.
Okay. Ah, what happened to you?
I missed the box.
Oh, so sad. Alright, look. Here it is here. So you change that into 19320. Kilo is 10 to the 3 grams, isn't it? Meter cubed is meter cubed. You don't want meter cubed. You want centimeter cubed. So you put a centi on the top and the bottom. So this becomes 19320 times 10 to the 3 times 0.01 cubed grams over centimeters cubed. So 19.32 grams per centimeter cubed. When did we do this? What lesson was that? Correct, first lesson. So long ago, back in September. It's now November. Continue? Yep. Right, some materials have a low density. Examples, please? What has a low density?
Gas.
Yeah, but particular examples, like what?
Iron.
Helium is the one I was thinking of particularly low density. Does anyone know this density? Probably not. It's 0.179 kilograms per meter cubed. This means that per unit meter cubed of volume of helium, there is 179 grams. It's pretty small, especially when you compare it to like gold. You know, 20 or 200,000 times smaller or whatever.
That's
Or
why-
sorry, 100,000 times smaller.
That's
yeah.
why you can compress it a lot.
Yeah, I suppose so actually. In these tanks, is it?
Yeah.
Because it comes out as a low density.
They use it for deep diving.
Oh yeah. Now how do they use it? I forget.
It
Do they breathe it?
They replace oxygen because it becomes toxic and replace it with helium. Well, they put oxygen but in really small quantities.
Is the helium replacing the nitrogen?
The nitrogen and oxygen, I think.
Some oxygen maybe. Yeah. Because what is it? You get nitrogen bubbles or something, isn't it?
Yeah, nitrogen bubbles.
Yeah.
And narcosis. And
That's it. Yeah, that's it. From the nitrogen. Yes, yes. So, what is a medium density? We've looked at high and low. What might you consider medium?
one liquid.
Yeah, like water. So, something like water, this is what I would call a medium density. It has 1,000 kilograms per meter cubed. And actually, this value is important in science. In fact, the density of water is so important, we often compare density of other things to that of water. So, for example, remember we said gold had a density of 19,000. Well, often we say that is 19 times more than water. So this gives us our next idea, which we call relative density. And this is where we compare the density to density of water. So the relative density S of an object is just the density compared to water. So that is simply the density of the object of the density of water. And also, what's the units of this S? What be the units? No units, yeah. Yeah, yeah. Ducky, you got that? No? Yeah? I mean, have you seen this before, or is this a new idea? What do you think? Have you seen it before? Or is this new? You've seen it before? No. No? It's new? Yeah? It's dimensionless. Now, one reason this is useful is for something called buoyancy. I'm sure some of you know this word. You know this word, Diego, don't you? What's buoyancy? Yeah, ability to float, yeah. So the reason it's important is because if the S is less than 1, what happens if you put in water? Are you sure? It floats. If it's more than 1, what happens if you put in water? Sinks. Hmm? Oh yeah, yeah.
And if it's 1?
It kind of moves with the water, I suppose. Yeah. I can kind of picture just floating around in the water, up and down. I suppose you're never going to get it exactly 1, because then it would be water. You know. Okay, so next I'm going to give you a table of values I'd like you to write down of different densities you'll need for some. Well, I suppose the questions should give you these values, but just in case they don't, here's a table of different examples of densities. So the first material we've done already, it's gold, so 19,320. Next one is silver, 10,500. Next one, nickel, next, salt water. This is what I think you were getting at, Zach. So salt water is denser than just distilled water. Does anybody know which part of the world has the saltiest water? Dead Sea. And this is why it's easy to float in it, because its density is greater. So the denser the liquid, the easier it is to float in. Has anybody been to the Dead Sea? No. Next one is fresh water, which is 1,000.
Is that distilled?
Distilled, yeah. Next, it's interesting, is ice. Now ice is 916, and when you think about it, this makes sense because ice floats, so the S should be less than 1.
So during the Halloween quiz, Diego and I were debating over that question with whether the ice cube would.
That's actually.
I said it would decrease because the mass of ice is greater than the
That's
mass.
actually, it's funny because I was kind of laughing to myself when Lorraine asked you that question, because I was thinking, oh, my poor physics students, they just missed this lesson where I actually give them that question. It's number 5 here, where I asked the class what would happen. So most people get it wrong.
They would say it stays the same.
Most people would say that either it increases or decreases. Hardly anyone says this stays the same. Yeah. So you missed that one. It was a little bit too early. Alcohol is 0.789. wood is 700.7. Now, it's only an average. Not all wood from all trees is obviously 700. In fact, there is one tree, what's it called, like black ash or something, I can't remember. There's one tree where the density is more than 1,000, which means if you put this piece of wood into the water, it would sink. Yeah, can't remember the name of it. It's maybe it's something like black ash. It must be one of those trees that, you know, the trees that really dry, and they can withstand forest fires, and they must be really dense, like really dense. But most trees obviously aren't like this. And the last one is air, just 1.2. Now that's not a lot when you think about it. You know, that means per meter cubed there's only 1 kilogram of air, which is not a lot. You know, you take that 1 kilogram away and you're dead. It's not a lot when you think about it. The difference between air and no air is only 1 kilogram per meter cubed. And how much of that is, so like, be about probably 200 grams. 200 grams per meter cubed. Something like this.
What's the other one? Is nitrogen, right?
The rest will be mostly nitrogen.
And then you have some small.
Some CO2, which we're working on increasing. Okay, continue. Yep, continue.
Yeah.
Oh, there is a material. What's it called? It's a gel. It was developed by NASA. It's the material with the lowest density.
Oh, is it kind of blue?
Some foam gel
Yeah,
stuff,
yeah.
isn't it? You've seen
Yeah,
it?
I know what you're talking about. And you put it on body can be waterproof.
I'm not sure how they use it. I thought they were going to use it in the space station for catching stray debris. I don't know how they use it, but it's extremely low density. Lower than air, I think. Okay. I don't think I'll do this one because it's not terribly important. Here's the ice cube question. A student places, I thought I was doing this later. A student places 10 grams ice cube in bottled water. The student closes the bottle. There's no free space. The ice cubes are held under the water. The bottle with the water is left out, and the ice starts to melt. When it's fully melted, what has happened to the water? Does it A, increase, B, remain unchanged, or C, decrease? And you remember your Halloween quiz?
B.
It stays the same. Yeah. So if you have ice in water, like that bottle of water, and it melts, then it stays the same.
So doesn't ice have a greater density than water should?
No, lower density because it floats.
Yeah, icebergs.
Yeah, yeah.
So the volume would be.
So when it melts, but it's also complicated.
The volume of ice is of the same mass of water to ice. The volume would be greater, wouldn't it? Because ice expands.
Yeah,
That's why
I need a picture. So like, if you picture that bottle, picture you put some ice in it.
Yeah.
So imagine you fill the water up to nearly the top of the bottle, and then you put some ice on the top and close the lid. So there's no free space.
So would it go down just a little bit because the volume of ice is.
Yeah, but we can actually calculate it. The ice that's, I see that, and the other problem is, okay, there's a couple of things that are happening. So the ice that's under the water, when that melts and becomes water, you're right, it'll drop. But then there's the ice above the water, and when that melts, it enters the water and would cause it to rise. And the two cancel each other out. You can calculate it. It's not a calculation on this course though, but you can calculate how much water you gain when the ice melts under the water, the height, and then you can calculate how much water you gain when the ice above melts, calculate that, and then you can calculate how much space you lose when the ice is taken out, and the two equal each other. You know, it does seem surprising though, because yeah, you would think it should shrink because the ice is lower density, but it's complicated because the ice is floating on the top. It's not fully submerged in the water. Yeah.
But in the case of the ice in the bottle that's sealed with no space,
Yeah, but
it would go down.
the ice isn't being pushed under the water. I guess I didn't make that clear. It's like, imagine you fill that water up to nearly the top, and you just leave enough space to have an ice cube floating on the top, and then you close the lid. Now, what you're saying though is right. If you were to hold the ice under the water,
Say the bottle is completely surrounding the ice and the water.
yeah, or even just have the ice glued to the bottom of the water,
Yeah.
then yes, when it would melt, the water would drop down.
What I see.
Yeah.
It's debating with him.
It depends if the ice is floating at the top or stuck to the bottom.
But the ice wall will never be stuck on the bottom.
Not without glue, no. Now, there's one question I want you to do. It seems like a simple question, but it can show you how you can get a little bit confused here. Some silver is actually not silver, but a mixture of silver and nickel.
Alloy.
Yeah, if you have any jewellery. Does anyone have any silver? Is anybody wearing any silver right now? No? Nobody.
No, this might be silver. I don't think so.
I don't think that's silver. Sorry, Saka. I can tell from there. Diego, nothing. Nothing. Oh goodness. Right. Anyways, if you have some silver, often it's not just silver. It's a mixture of silver and nickel. Yeah. So my question is, what is the density of a mixture which is made of 10 grams nickel and 1 gram silver? So what's the density of this? Will it be the density of nickel? No.
No.
Will it be of silver? No. It must be somewhere in between the two.
So the biggest one minus the smaller one.
Let's see what you can do. Give it a calculation, and then I'll give you the answer. See if you can get this.
Do you want the answer in grams per meter cube?
Not kilograms per meter cubed, the usual.
Syntax is weird.
What is it? Are you giving me kilograms per meter cubed or grams per centimeter cubed? How are you giving?
Residence, sorry.
Oh, relative density's fine. What did you get?
945.
Sounds believable.
800
What did I say the density of nickel was?
8,900.
8,900. So,
And silver was 10,500.
9,000.
Okay, let's have a look. Good job. This sounds right. Let's have a look. So look. Okay. The density of the mixture is equal to the mass of the mixture over the volume of the mixture, obviously. The total mass we know, it's 11 grams, 0.011. The volume, we don't know. It's the volume of the nickel plus the volume of the silver. But we don't know how much we have of each, do we? Now, we can use this formula, density is mass over volume. So then that means volume is mass over density, right? So I can change this into 0.011. So volume of nickel is mass of nickel over density of nickel. What is the mass of the nickel? I said it was 10 grams, didn't I? And what was the density? 8,900? Plus the mass of the silver over 10,500. So what do you get when you bash this in the calculator? Is this not what you did?
$9,025.02.
9,025.
25.
So that would be 9030 kilograms per meter cubed. But if you wanted to, you can also say that's 9.03 grams per centimeter cubed, or you could even say that's 9.03 relative density, which is how you gave it, Dorian. What answer did you get? 9,000?
And 45.
And how did you do it? Because you were quite close. What did you do? Like, you were very close, so why did you do it?
I used fractions. 1 for 11 and 10 for 11.
You found the average.
Yeah, I would have thought that should
I was
work.
doing that. You use 10 over 11 and 1 over 11.
And does that not give the same answer?
Yeah, because 9.945.
But wouldn't that be the weighted average?
Yeah.
And this is just saying there's equal parts, isn't it? No, because it's 0.01 and 0.01.
That's an interesting way to do it. I guess it doesn't work, or at least it's not exactly the same answer. So you said what were the two fractions you used?
1 for
1/11,
and 10 for
10,
11.
10/11s. It was a good idea. Doesn't seem to work though. This is definitely the right way to do it. This is how I've seen it done in the exam as well. I don't know. Maybe, so you chose to use the mass as the weight, like 1 over 10 and 1 over 11. But maybe you get the right answer if you use the volume.
Yeah.
You know, like if you got the volume of each and used that as the weight. Doesn't seem to work for mass though. Yeah. Okay. But I would like to see why it doesn't work. Can I scroll down? Yeah. So a couple of you had the idea of saying, well, what about the density of the mixture is basically what you said, it was M1 over M1 plus M2. This density of the first one plus M2 over M1 plus M2 density of the second one. This was your idea. So that's equal to M1 density 1 plus M2 density 2 over M1 plus M2. Density is mass over volume. So mass volume is not part of this calculation. Just kind of a bummer.
What's the mass? I'm doing
Yeah.
0.001 gram of soda.
Yeah.
Loss.
I think part of the reason it's not working is because volume doesn't really come into this formula, and volume is important for density. Whereas with my one, I'm saying density of the mixture is mass 1 plus mass 2 over volume 1 plus volume 2, which I said was mass 1 plus mass 2 over. Yeah, I think the problem is this formula has no V in it, whereas my one has M and V in it. M1 over density 1 plus M2 over density 2. It's kind of similar because I have M1, M2 on the top. You had it on the bottom though. And I also have an M1 and an M2. But I have 1 over density and 1 over density. So 1 over density of the mixture equals density 1 over M1 plus density 2 over M2 over M1 plus
Or
M2.
you could say
Interesting. Okay, I see what's happening here. 1 over M1, 1 over density 1 plus 1 over M2 density 2 over M1 plus M2.
in 1 over density 2.
Oh, sorry. So it's almost like your idea would nearly work if it was for 1 over density. It's almost like saying 1 over the total density is nearly the weights of 1 over each of the densities. I don't know. I think if I could play with this a little bit more, I would kind of get it like that formula in electricity, maybe. You know this one? It's kind of looking like this. So perhaps density behaves like this. It's more about 1 over rather than it. But this is very dangerous and messy. We'll just stick to this way. It's the safest thing to be doing. Okay. Right. Yeah, that's all. So we've got a few minutes left. You can get a start on this new chapter. How many questions are there? Probably not too many.